So hello to everybody. This is again algorithmic design, because of the algorithmic design, and during the last lesson we were trying to solve some exercises. So my idea for today is to go on. So spend the whole lesson to trying to solve our exercises. So to do it, let me move to our tablet. Well, first of all, I have to say that many of you contacted me asking some question about the homework. So keep going. Okay. So I really think it's important for you to ask questions and try to understand what's going on there. But as usual, I always said, it's important also for me. So let me know if you can. Well, first of all, let me go. If you can list me, so send me an acknowledgement on the live chat, and secondly, please. On the chat itself, write all the questions you may have concerning the homework. Okay. And so let me move to the tablet. Oh, by the way, thanks to one of your colleagues which asked the right question, I noticed that during my last lesson I have two typos. So let me first of all fix those typos. And the typos was about the solution of equation T1. If you remember, the equation T1 was this one. So let me write. I cannot write it. Oh. Let me write it. This is it. This is not what I want to do. This is what I want to do. So the equation 1 was this one. From color. This color. The equation 1 was this one, and well, probably not really this one, but something similar to this one, and was this one actually, and we were trying to solve it by substitution. At some point I end up in dealing with this equation, and I impose the condition that this part of the equation, so the double underlined part of the equation is smaller than 0, just to apply the substitution method. And by copying it, I replace a log 2 by log 2 base 2 with a log n base 2, which of course is wrong. So let me change it, and 2. So since and 2. Now, since log 2 base 2 is 1, of course, we are basically asking that under this condition is equivalent to asking that c is greater or equal to c prime. Okay. And this is the first typos, and the second typos was about the conclusion. I don't know why. Of course, we always dealt with n log n equations, and I don't know why I wrote big O of n. Of course, this is wrong, and it should be big O of n log n. Okay. So this is the typos concerning the previous lesson. So after that we move to this equation, I hope you can see it through this equation, which is a little bit weird, and the last time many of you asked many questions about it, especially because it's unclear at the beginning what's going on here. So let me just do everything concerning this equation from the scratch, okay? And we did exclusively the goal of the exercise was to solve the equations by using both the recursion tree and the substitution method. So the last time we had only time to see the recursion tree method applied to this equation. Let me do it from the scratch, and then we will see what's going on with the substitution method. Okay, so let me open another note. Okay, so the equation was, again, let me rewrite it. The equation was equation 2 in the last homework, and the equation 2 was this one. So we have two recursive calls. The first one deal with the ceiling of half of the original input, while the other recursive call is applied to the bottom of half of the original input. Okay, and the complexity is theta for each. To prepare its recursive call is theta of 1, of course. Now, let me try to solve it by using the recursion tree. So to do it, first of all, let me try to understand what's going on. Okay. So let's assume we are dealing with I don't know, with so for example, let n equal to 9, and let's try to understand what's going on here. So if n is equal to 9, the first recursive call, so the recursive call dealing with the ceiling of n divided by 2, will end up in performing. So here we have at the beginning, at the top of our recursion tree, in this specific case, we will have 9. So the first call will deal with 9 elements. Okay. Then the first call, which is the first call, which now represent on the left, will deal with what? With half of the original, the ceiling of half of the original elements. So the ceiling of 9 divided by 2 is of course 5. What about the other call? Well, the other call will handle half the original, the floor of half of the original input size. So since the input size was 9, we were dealing. So the other call will deal with 4 elements. Okay. Now, of course, we can extend the tree, and from this call, so from the leftmost call, with the left call, we again need to repeat all this process. So the first call will deal with the ceiling of half of this. The ceiling of half of this is of course 3 elements. while on this branch we will have 2 elements. And what about here? Well, here we will have the seeding of half of this element, but half of this element is 2 by its own, so 2, and again here 2. And again here we may need to keep going with the recursion. So from this call, the first call will be concerning 2 elements, which is the seeding of 3 divided by 2, and here we will have 1 element, here we will have 1 element, 1 element, 1 element, 1 element, and so on and so forth. Okay. Now again, so all the calls dealing with one single element we may assume conclude the computation. Of course, we don't have let me move my face on the other side. We don't have the base case for the equation, but we may assume that the base case is about n equal to 1. So this is enough. What about so all the calls dealing with one single element will end up of their execution. What about this single call? So this call again required to split the computation into 2 sub-branches. So these 2 will become 1 and 1 again. So as you can see from this example, our tree is not balanced. Okay, and so it's not, well, it's balanced, but it's not complete. So the 8 of this branch, so the length of the leftmost branch is 1, 2, 3, 4, and 5. So this is 5. What about the length of this branch, of the rightmost branch? Well, the length of the rightmost branch is 1, 2, 3, 4. Okay, so here we're dealing with a not balanced tree, but a tree which is not complete. So how can we deal with this object? Well, to deal with this object, to understand the complexity of this object, of course we can upper bound the 8 of the tree and lower bound the 8 of the tree. So if all the calls dealing with the seeding of half of the original input size will be on the left, as we did on this example, the longest branch will be the leftmost. On the other side, if all the call dealing with half, the floor of half of the original size will be the right call on the tree, the shortest branch on the tree will be the one on the right side. So the rightmost branch will be the shortest one. Okay. This is just to figure out what's going on. So now let's try to generalize it. We saw an example dealing with n is equal to 9, but of course we want to compute the complexity with respect to n, so with respect to the input size. Okay, so and again let me draw a tree in which I want to represent not the complexity of each. I don't want to represent in the tree I'm going to write the complexity of each call, but I'm going to represent the number of elements which are dealt by each call. Okay, so at the root of my tree I will have n. So this is the first call, and on the left side I will deal with with the ceiling of n divided by 2. And on the right side I will deal with the floor of n divided by 2. And these are the two recursive calls represented by the equation. Okay. Now, of course, from this point, I need to again. Well, let me reduce the size of my arrow. I need again to perform two recursive calls, and the first one will be n divided by 2 divided by 2 floor, and the second one will be n divided by 2, so n divided by 2 divided by 2 ceiling. Okay, so since the number of elements on this call is the ceiling of n divided by 2, and then I need to repeat two recursive calls, the two recursive calls will be applied to this number, and that's why here we have these two stuff. What about this call? Well, this call of course is almost the same, so will be the floor of n divided by 2 divided by 2 ceiling, because remember on the left side we always deal with ceiling, let's say, recursive call, while on the right side again we will have the floor part, and this is it. Okay, now of course you keep going until you end up with 1 here, and you keep going until you end up with 1 here and on the wall level. Okay, now the longest, for sure, since on the left side we are dealing with the ceiling and on the right side we are dealing with the floor, the longest branch will be the one on the left, and the shortest branch will be the one on the right. Now, how long is the one on the left? Well, of course, it's easy to prove that, well, of course, first of all, if n is a power 2, all these ceilings are totally useless, and all these floors are totally useless, because you keep divided by 2, and the power 2 is, of course, divisible by 2. So any reminder, so the ceiling of something divisible by 2 is exactly that number divided by 2. So if n is equal to some power of 2, you end up in dealing with something without ceiling and floor. Okay. Now, so how long is this branch? Well, let's try to imagine that this is divisible by 2. Well, in that case will be of course logarithm base 2 of n. Okay. Now, how far are we? So how far is n from the next power of 2? So let's try to figure out the nearest power of 2, which top n. Well, of course, it's easy to prove that between n and n multiplied by 2, you have a power of 2. I mean, this is almost straightforward property. It's quite easy to prove. Okay, do it by your own. It's not really that difficult to prove it. So we may say that this branch for sure is shorter. This branch for sure is shorter than the logarithm base 2 of 2 multiply n. N is smaller or equal than the next power of 2, and for sure is smaller than 2 multiply n. So, well, this is a straight so is smaller, not smaller or equal inequality. So strict inequality. So what about the right side? Well, the right side is almost the same. So again, if n was a power of 2, all this branch would be exactly the same as avoiding the floor. So we simply, to know to have a lower bound for this branch, we simply have to search for the largest power of 2, which is smaller than n. And for sure this is larger than n divided by 2. So the maximum length of this value of this branch, maximum length of this branch is for sure larger than the logarithmic base 2 of n divided by 2. Okay? So now we have a complete view of the tree, knowing that for sure up to this level, so up to the right, since this is the shortest branch on the tree, up to the level logarithm base 2 of n divided by 2, up to this level, the tree is complete. Okay, so now let's try to figure out the complexity, the overall complexity of our algorithm. Well, for each recursive call, if you remember, we had a theta of 1 complexity. So now we may say that well, we for sure we have a tree done in this, a recursive tree done in this way. The first call will cost something which is in theta 1, so let's say c. The second call, so the second level will cost again for each call c. The third level again will cost something related, something in theta of 1, so again c, and so on and so forward. So the ith level, so the ith level, so if this is the ith level, will cost, well, so at level 0 we have 1 element, at level 2 we have 2 elements, at level 4 we have 2 at the power of 2 elements, and so on and so forward. So at the ith level we have the complexity will be c, so the time spent to solve the ith level will be c multiplied by 2 at the power of I. And this is the cost, so this is the cost of the I. Of the I. level. Okay. Great. Now, of course, we have to sum up all the levels. So the complexity, the overall complexity will be at least will be so t to the of n is for sure greater than what? Well, the rightmost branch is the shortest one, and we said that since it's the shortest one, the tree is complete up to the level corresponding to the length of the shortest branch. Okay. Since the length of the shortest branch, which is the rightmost, is at least greater than this value, we may say that the complexity of T2 on n will be for sure greater or equal than what? Than the sum for all the levels going from 0 up to the last level of the rightmost branch, which is for sure greater than log 2 of n divided by 2 of what? Of this value. So at each level we will have c multiplied by 2i. Okay, and so what's this? So let me copy this stuff and move to the other page. Okay. This is it. So again, what's this? Well, let me apply some algebraic changes. So if I move outside the sum c, I end up with c multiplied by this stuff. This is a geometric series, so we can solve it simply by writing 2 multiply at the power of logarithm base 2 of n divided by 2 plus 1 minus 1 to minus 1. Okay, this is because this is a geometric series, of course. Now this is 1. Well, this is again more or equal than c multiplied by 2, and now of course I can rewrite this logarithm as a difference between logarithms. So let me write it as logarithm base 2 of n minus logarithm base 2 of 2 plus 1, and of course minus 1. Now logarithm base 2 of 2 is 1, so this is equivalent to this, and I can remove them. So I end up with c multiplied 2 at the power of logarithm base 2 of n minus 1, and of course this is equivalent to n, so this is smaller or equal than c multiplied n minus 1, which is of course belonging to theta of omega of n. Okay. So since I discovered that the least amount of computation that I need to perform to solve T2 of n is greater of Cn c multiplied by n minus 1, I can conclude that T2n belongs to omega of n. Okay? Now this is a lower bound for the complexity of T2, but we need to evaluate an upper bound for the complexity of T2. So let me go back again to the tree. Now we have an incomplete tree, of course. So incomplete by incomplete, I mean is not complete, of course. So we may try to upper bound the complexity by assuming that all the levels reach the level of the length of the longest branch of the tree. Okay, so the leftmost branch is the longest on the tree. So for sure all the other levels ends before that level. Well, doesn't end after that level. So what if we assume that all the levels ends at that level? Well, in that case, we have an upper bound for the complexity of, we are just overbounding, over approximating the complexity of T2 of n, but it may be okay. We will see. So this is for lower bound. Let's try to see what's going on with an upper bound. So what if we try to deduce an upper bound for T2 of n? Well, to deduce an upper bound, of course, we need to find something greater than the function we are trying to study. And something greater will be something, for instance, the tree will be done by assuming the tree complete at the longest branch on the tree itself. So this is done in this way. So if I sum up the complexity of each level, which is c multiplied 2 at the power of I, for the level from the level 0 up to the longest, so the length of the longest branch of the tree, which is logarithm base 2 of 2 multiplied n, I end up to over approximate the complexity of T2. Okay, and again, quite quickly, this is I'm just keeping some passages, so this will be logarithm base 2 of n plus logarithm base 2 of 2 plus 1 minus 1, and this is for sure greater than c multiplied by, so all this stuff is 2, and so I can rewrite this power as a multiplication between 2 at the power logarithm base 2 of n multiplied by 2 at the power of 2. So 2 at the power of 2 is 4, so I can rewrite everything up there into c multiplied by 4 multiplied by 2 at the power logarithm base 2 of n and minus 1. Let me go back, because probably, oh, this is, of course, this is not a 1, but it should be a c. In any case, is again a constant. So what about this equation? Well, this equation, of course, is c multiplied 4 multiply n minus c, which this equation belongs to, and let me move my face again. So this equation belongs to big O of n. So now we discover that our T2 belongs to omega of n and belongs to big O of n. So T2 of n belongs to theta of n and this is the solution. So this is the solution of the equation T2 of the exercise number, I cannot recall the exercise, but you know it, done by using the recursive tree. Okay. Now let me move to the. Let me move to. Are you still there? Can you send me an acknowledgement just to know that you are there, please? Because I cannot see anything moving on my computer. Okay, let me move on meanwhile. So now let's try to prove that, and this is quite interesting, let's try to prove that T2 of n belongs to theta of, well, first of all, let's try to prove that belongs to big O of n by using substitution method, which I recall you is basically an induction proof. Okay, so first of all we need to select a function in big O of n. Okay, so a possible function for belonging to big O of n, of course, will be, so step 1, select a function in big O of n. And of course, since in our equation, let me go back to the equation. This is the equation. In our equation we have a theta of 1 here. We need also select a representative for theta of 1. And as a representative for theta 1, let me select 1. I mean, it's the easiest selection. So, and select a representative for theta of 1 equation. Okay, so let's say we will deal with for instance Cn belongs to theta big O of n, and n1 belonging to theta of 1. Okay, this is my selections. I mean, it's, they are totally, how can I say, they are done. I mean, I don't have any algorithm to select them. I just choose them as I want. Okay. Now, after that, so step 2, we need to assume that, well, that T2 of, well, that for all m smaller than a given n, well, T2 of m And now, since I want to prove that my equation belongs to big O, here I need to place something greater than T2 of m. So I assume that T2 of m is smaller or equal than what? Then the function I have selected. So the function is selected with respect to n. Since here I'm dealing with m, of course this will be Cm. Okay, this is an assumption. The inductive assumption. Okay, and prove that T2 of n is again smaller or equal than Cn. Please notice I really need that my final conclusion is this one. So I'm not satisfied with a conclusion in which my T2 of n belongs to something similar to this equation. I really need this inequality. Okay, so now let's try it. So let's try it for the specific case. So the specific case is the equation we had at the beginning. So the equation we had at the beginning is well, let me move to the next paper. So the equation we had at the beginning was T2 of n is equal to T2 of the ceiling of n divided by 2 plus T2 of the floor of n divided by 2 plus, and here we had theta of 1, but we selected in step number 2 1 as a representative for the functions there. So by using this equation we need to prove this inequality. Okay, so basically we know that T2 of n is equal to all this stuff, and we want to prove that this is greater than this stuff. So T2 of n divided by 2 plus T2 of, again let me rewrite everything here, plus 1. But this object, well, I can do it by using the original equation just to now this object, of course, this object of course is smaller than n. So here we are dealing with a recursive call in which the parameter is smaller than n. Since in our assumption we said that for all the n smaller than n this equation holds, this inequality holds, we may conclude that this call takes at least Cn divided by 2 ceiling times to be solved. Okay, and of course for this very same reason we can conclude that this call takes time at least equivalent to n divided by 2 floor, and this is 1. Now all this stuff of course is C multiplied by what? By the sum between the ceiling of n divided by 2 and the floor of n divided by 2. But this is of course n. Okay, because this is another approximation of the, well, this is of course the ceiling, so the next integer with respect to the n divided by 2, and this is the previous integer, so the integer which comes just before n divided by 2. So if I sum up them, I end up with n again, and so this is greater or equal than c multiply n plus 1. Okay. Oh, fine. So we discovered that n2 of that, t2 of n is smaller than c multiply n plus 1. So we can conclude that t2 of n belongs to big O of n. No, we cannot. Why? Because our goal was to prove this inequality. And by proving this inequality, thanks to the induction, we may conclude that this condition holds for all the integer, all the natural numbers. And because of that, we can conclude that we have a constant c, and we have constant c such that c multiply n upper bound our t for any n. And so in that case, we may conclude that this belongs to big O of n. But here we haven't proved this inequality. We have proved this inequality. So by using this inequality, we cannot conclude anything, because it's different from what we want to prove. Okay, so this does not prove t2 of n belongs to big O of n, because Cn plus 1 is not smaller or equal than Cn. Okay, so just to use some colors, this stuff is different from what? From this stuff. Okay, so what's the problem here? Well, the problem is that we selected the wrong representative for big O of n. So the problem is that we selected the wrong for big O of n, sorry. Of course, as you see, it may be the case that you are not able to prove anything. So this doesn't mean that your function does not belong to big O of n. We already proved that this function belongs to big O of n by using the recursion tree, but I mean, if you are only focused on proving it by using the substitution method, you might figure out the situation in which this function does not belong to it, simply by observing that you weren't able to prove it by using this selection. And this is not the case. I mean, if you are able to conclude the proof by substitution, you can conclude that your function belongs to the function belongs to the family that you guessed. Otherwise you cannot conclude anything. And this is a case. We weren't able to prove that T2 of n belongs to big O of n by using the selection we did, but you cannot conclude that this is not the case. So the problem here was that we selected the wrong representative for C. If you for big O of n, if you remember, we selected C multiply n. Now let's try to select a different representative. For instance, in this case, let us choose C of n minus d as representative for big O of n. Well, of course, this is a different representative with respect to the previous one, but still is a representative for the family. Okay, so by d I mean a constant again. So C and D are both natural constants. Now let's try to see what's going on here. We have a T of 2 smaller or equal than well, let me move to another page. Here we have T of 2 of n equal to let me rewrite the equation we saw before. So this is n divided by 2 plus T2 of n divided by 2 floor plus 1. Well, this is smaller or equal, of course, to... Now, since this is smaller than n, we can apply our assumption, and our assumption is done on this equation. So, for all we are assuming that for all m smaller or equal than n, T2 of m is smaller or equal than Cn minus d. This is our assumption. So since this is smaller than n, we can conclude that this is C multiply n divided by 2 floor minus d plus, again this is smaller than n, so this is C multiply by floor of 2 of n divided by 2 minus d and plus 1. So this is for sure smaller than equal. Again, summing up this stuff with this stuff, we end up with C multiply n as we did before. Here we have 2 minus d2 minus d2d, and here we have a plus 1. Okay, now as soon as so if this stuff is smaller than smaller or equal than 0, so if 1 minus 2d is smaller or equal to 0, then we can T2 of n is smaller or equal than Cn . Which is exactly what we want to prove. So this Cn, oh no, I miss it. Sorry, this is not the case. Let me. This is not what we want to prove. We want to prove is the following stuff. So if 1 minus d is smaller than 0, then this stuff is smaller than Cn minus d. Okay, so this equation, this stuff of these terms, is exactly what we saw. This shouldn't be n, but should be m, of course. Is exactly what we saw here. Okay. So since this is exactly what we saw here, we can conclude by induction that this holds for all the value of n, and so we have proved that T2 of n belongs to big O of n. Okay. Of course, we are missing the part in which we prove that T2 of n belongs to omega of n. Let me do it straight away. So yeah, we need to prove proving that T2 of n belongs to omega of n by substitution. So let me select a representative for this function, for this family. A representative could be Cn, for instance, as we saw before. So Cn belongs to omega of n. So now, since I want to prove that this function belongs to an omega, an omega of something, of some function, I need to prove that T2 of n is greater or equal to what comes after that. So now, this can be done this way. So let me rewrite the function, the equation. This is T2, this is T2 again, and let me leave as it was the representative for the omega function there, for the theta function there. So for sure this is greater or equal to, again, yeah, I need to assume that this call is greater or equal than what? Than C of this stuff, C of this stuff plus 1, which is greater or equal than C of n plus 1, which is of course greater or equal than Cn. Okay, so now this equation, which is the representative we selected for omega of n, is what we got here. And so by induction we can prove, basically prove that for any value of n we have this function belongs to this function, so T2 of n is greater or equal than this stuff here. So we can conclude that T2 of n belongs to omega of n. Let me write it. So T2 of n belongs to omega of n, and because previously we proved that T2 of n belongs to big O of n, and also belongs to theta of n. And this is it. Okay, so of course I spend a lot of time trying to explain what's going on, but I mean it's quite easy to do it, I mean, in 3 minutes. Okay, once you understood what's going on, repeating all these steps is almost mechanical. In the last example, so the example of T2, the toughest part is to figure out that the good representative for our function, for our family, is this one. Okay? And this is it. Well, of course, you may also provide not strict result by using this function. So by using this strategy, this solution method. So for instance, you may also prove that T2 belongs to big O of n squared, which is not wrong, of course, because if it belongs to big O of n, it also belongs to big O of n squared, but it is not the stricter set of function to which T2 of n belongs. Okay, so let me rephrase it. By using substitution method, by using in general, by using substitution method, you can prove that T2 of n belongs to big O of n squared, or big O of n cube, or any function which tops n, of course. This is not wrong. Because big O of n is a subset of big O of n squared, of course. However, this is a this is of course approximation, but this is of course complexity. Bound, let's say. Okay. Okay, this is enough. Let me move to something different. Let me see what's going on here. Oh, okay. Let me try to solve a different equation, which is again interesting from a certain point of view. I will solve it. Well, I will solve it. First of all, I will try to solve it by using recursion tree. So let me consider the equation t of n equal to t of 1/5 of n plus t of 3/4 of n plus, and here let me say theta of n. Okay, so let's focus on this equation. This is quite weird in a sense, and let's see why. Let me see why. This is weird because the tree is totally unbalanced. So trying to figure out what's going on here seems to be a mess. Okay, and let me write some. Let me make an example of a tree. Example. And equal to, I don't know, here, let me see, 20 for instance. So if I start dealing with 20 elements after the first call, so after this call I will end up with 4 elements. Well, probably 200 would be better. 40 elements. Here I will deal with 50 multiplied 3, so 150 elements. Then here again I need to divide by 5, so this will be 8. And the second call, so this call from this element, from this node, my 3 is divided by 4 multiplied by 3, so this is 30. And what about here? Here I will have 1/5, so 30 again. And here will be so divided by 4, which is a weird number here. So 12, 3, 30, which is what? So 30 plus 30 divided by 4, which is about 8, let's say. So this is 7 dot something else, I don't know, multiplied by 3. Okay. So this is 91 multiplied plus 21, which is 112. So let me remove all this stuff. This will be 112. And if you keep going, you can understand how it's quite difficult to understand what's going on here. I mean, we really cannot figure out what's going on with the number of elements in each level, and all the branches are different in size, in length. So let me try to simplify all the things by generalizing, okay? And let me say that instead of writing every times 1/5, I will write alpha, and instead of writing 3/4 every time, I will write beta. Okay, and let me write the tree, the general tree. So we will start with n elements in the first call. So the leftmost, the left call will end up in dealing with alpha multiplied by n element. The right call will end up, so the second call will end up in dealing with beta multiplied n elements. And if we go down, we see that this is alpha multiply alpha square multiplied by n elements. So again we multiply n by alpha, by alpha again. So we multiply alpha n by alpha, we end up with alpha square multiplied by n. And what about this call? What this call will be alpha multiplied by beta multiplied by n. And here, since we are moving on the left side, so the first call will be this stuff multiplied by alpha multiplied by beta multiplied by n, while the right side of this subtree will deal with beta square multiplied by n elements. Now let me move down here from exclusively from this node. Well, on the left side we will see alpha square multiplied by beta multiplied by n, and on the right side here we will see alpha multiplied by beta square multiplied by n. What about this call? Well, this call we will have the left side, we have to multiply by alpha all this stuff, which is alpha multiplied beta square multiplied by n, while on the right side we will have beta cube multiplied by n. Now, as you can see here, we basically at each level, so let's take the ith level, on the ith level, all the nodes but let me copy on another slides. It's a mess, I didn't know the stuff in this way. So on ith level, all the nodes, well, I'm missing on the ith level, all the nodes contains alpha j multiply alpha at the power of j multiply beta at the power of I minus j elements. Okay, it's quite easy to see, because every time I move from a level to the next one, I either multiply the value by alpha or by beta, so I'm increasing by 1 the power of either alpha or beta. Now let's have a look at this element. Why this element has this configuration? Why the number of elements in this recursive call is alpha square multiplied by beta? Well, the motivation for this is due to the fact that basically I selected from the root, moving from the root up to this node, I selected twice the left branch and once the right branch. Okay, let's see. Left branch, right branch, left branch, and that's why I end up here. Let's see, this, for instance, this what about this node? Well, this node I selected once the the left branch and twice the right branch. Left, right, and right. This node, which is of course different from this one, but has exactly the same number of values, is obtained by performing twice the right branch and once the left branch. as a matter of fact, right, left. Okay? So the point is, since we know that at the ith level we need to perform, to reach the ith level we need to perform I moves. How many ways I have to select two right moves over 3 possible moves at the third level? So I want to know how many elements having alpha multiplied by beta square multiplied by n. How many nodes having these elements to deal with I have on the third level? Well, to know it, I simply need to know in how many ways I can select two right moves over the 3 possible moves I can do. And I have many ways to do it. Well, of course I can simply select twice at the beginning, twice right moves, and then one alpha move. Or I can select an alpha move and then twice the right move. Or I can select a right move, then a left move, then again a right move, and I end up exactly in that situation. So the number of nodes having at the ith level having this configuration, okay, is the number. So the number, let me rewrite it just to fix point it. The number of nodes on the ith level having alpha j multiply beta I minus j element to deal with is the number of possible way in which we can select j sorry, not j, but yeah, j moves, j alpha moves, so j left moves over I total moves. Okay, let me move my face again. Oh, I cannot move my face anymore. Now, so how many possible ways do we have to select j left moves over I total moves? Well, this is the So what? This is the binomial coefficient okay. So to know how many ways we have to select j possible left moves over a total of I moves, of course with j smaller or equal to I, we can use the binomial coefficient, meaning that at each level I we have let me copy it to another slide. So on each level I we have let's try to count how many elements we are dealing for each level at each level. So at each level I we are dealing with what? With the sum for j going from 0 up to I of what? Since we are dealing with the ith level, of course we have I possible moves with the binomial coefficient of j over I of alpha j multiplied by beta I minus j multiplied n. Sorry, not m but n. So this is the total number of elements we need to deal with at the ith level of our Recursion tree. Okay. Now what's this stuff? Well, this is a very famous, let's say, equation, sums. And just try to remember what's useful for the binomial coefficient. Well, binomial coefficient is useful for many things, but I mean the most famous one is to compute the power of a sum. Okay, so if you are trying to compute the ith power of alpha plus beta, you end up exactly with this sum. So this stuff is basically as alpha plus beta at the power of I. Well, still missing multiplied by n, of course. Okay, so since we know that for each level ith we have this number of elements, we need to deal with this number of elements, we can overestimate the overall complexity of our algorithm. Let's go back to the equation. So this stuff is just to see what's going on. This is the equation. So at each recursive call we are dealing with theta of n operations. So if we know how many elements we have at each level, we know exactly how much the level costs from the asymptotic point of view. So let's try to deduce another approximation for our complexity. So for sure, T of n, oh no, this is not the correct equation, let me go on. Okay, so T of n for sure is smaller or equal to what? To the sums for each level, and we don't know the height of the tree, but let me over approximate it. Let's say we are dealing with an infinite tree instead of a tree which has an 8. Okay, so let me say the tree doesn't end, and we want to sum up the complexity of dealing with this infinite tree. Okay, this is another approximation, of course, of the total complexity, but let's see how much is it. So I was saying for each level going from 0 up to the infinity, assume this is, of course this is not the case, the tree is finite, but let's assume it is infinite, just to have another approximation of the complexity. For each level we have to sum up alpha plus beta I multiply n. Okay, now let's have a look to this sum. Of course this n can be moved outside the sum because it is not dependent on I, but let's focus on the part, let's for a moment avoid to think at this n, and let's have a look at this sum. So this is a geometric series, and we know how to solve it. Okay, and in particular, if alpha plus beta is smaller than 1, we know that this series converges. Okay, and well, diverge for everything for alpha plus beta greater or equal to 1, but for alpha plus beta smaller than 1, well, between 0 and 1, okay, it converges, and in particular it converges to, so Tn, well, let me because of the convergence of the geometric sum, but series, geometric series, Tn is smaller or equal of what? Well, this geometric series converges to alpha plus, well, not alpha plus beta, but 1 minus alpha plus beta, well, 1 divided 1 minus alpha plus beta. This is the convergence of this series. Okay, and this is multiplied by n. Well, the convergence of this series, of course, exclusively occurs whether this is smaller than 1, but alpha was oh, this is a mess, let me move down this stuff. delete something here. I missed to because the counters are series, so let me write here alpha plus beta is equal to 1/10 plus 3/4, which is smaller than 1. Okay, we know that this converts to this stuff, and since this is a constant, so this stuff is a constant. This means that T of n belongs to big O of n. Okay? So basically we have just proved that our initial equation, which was, let me go back, this one, belongs to big O of n, which seems to be weird because at the very beginning, just for the first call, we are spending theta of n, and then of course we have many other calls. So apparently by looking at this equation, one may be pushed to think that the complexity of this equation is greater than theta of n, but actually by performing all the computation and by over approximating the height of the tree, assuming that it is infinite in size, which is not the case, of course, we end up in concluding that our complexity is smaller or equal than something which is constant multiplied by n. So the complexity of our equation is for sure big O of n. Now, can we lower bound it? Of course we can, because the first call, just the first call of our recursive call cost theta of n, so cost something which is in omega of n. Okay, so the first call, just because of the first call, our recursive call, our equation belongs to omega of n. We just proved that it also belongs to big O of n. So T n belongs to theta of n. Okay, it's really interesting about all this stuff is that we basically prove something in a really general way, and we have a new theorem here basically. So we started from a simple example, which was the equation in particular, this one, but all our reasoning was done on alpha and beta, and the only condition we imposed was to have the sum of alpha and beta smaller than 1. So this means that here, just to solve this problem, we prove a new theorem. So let alpha and beta be two natural number such that be two natural numbers if alpha plus beta is smaller than 1, then t of n equal to t of alpha n plus t of beta n plus theta of n belongs to theta of n. Okay, so every time you have a recursive equation written in this way, so written as which has two recursive calls, and the sum, and each recursive call is dealing with a number of elements which is the original number of elements multiply an alpha, and the second call is the a recursive call dealing with a number of elements which is the original number of elements multiply beta, and alpha plus beta is more than 1, then this equation belongs to theta of n. And this is a way to easily figure out strange, let's say, equations, because as you can see here, this is this equation bring a non-complete tree. So it's quite hard to see what's going on, and as you saw, we spent half an hour to prove all the stuffs. Okay, so this is enough of this lesson. I saw that you sent me some question about what we did today. So my idea is to have an interactive session on Teams. So probably for the next lesson will be done in that way. So I really need you to collect all the questions you have, and I will send you an invitation for a new group on Teams, and we will have just a question time on it. Okay, so the next lesson will be done in that way. So the next Monday we will have a lesson done on Teams, but on Tuesday we will have a normal lesson on a new topic. Okay, so during this weekend, please collect every possible question you may have about all the homework, all your problems with installing the software. I'm not able to compile it, everything. Please collect all of them, and on Monday morning we will try to answer all that question online by using Teams. Okay, so thank you so much for the attention, and enjoy the weekend, and see you soon then. Bye.